Tonight, we are going to examine something that feels ordinary, yet is quietly misunderstood: darkness. On Earth, even in the quietest midnight, or inside a closed room, darkness is never truly complete. There is always light present, though often too faint to notice at first glance. Light from distant cities reflects off particles in the atmosphere. The moon, even when not directly visible, contributes subtle illumination. Starlight, though weak, continues to arrive from across vast distances. And importantly, Earth's atmosphere itself scatters light in all directions, ensuring that some portion of it always reaches us. To understand this more clearly, consider a simple observation. When you enter a dark room, it initially appears completely black, yet after a few moments, shapes begin to emerge. This is not because new light has entered the room, but because your eyes are adapting. The human visual system is remarkably sensitive. It can increase its ability to detect light by thousands of times in low light conditions. Specialized cells in the retina, known as rods, become more active, allowing us to perceive even minimal light. Here is a useful way to think about it. What we commonly describe as darkness is not the absence of light, but the presence of very little light, combined with heightened sensitivity. In scientific terms, this is a low-light environment, not true darkness. This distinction is important because it reveals a limitation in our everyday experience. We assume we understand darkness because we encounter it daily, but in reality, we have never experienced its complete form. A small but important teaching insight emerges here. Human perception is not a direct representation of reality. It is an interpretation shaped by biological systems. In the case of darkness, our eyes and brain work together to fill in gaps, allowing us to function even when light is scarce. This creates the illusion that darkness is something we are familiar with, when, in fact, we are only experiencing a softened version of it. This leads us to a fundamental question. If every environment on Earth contains at least some measurable light, then what does true darkness look like? Not reduced light, not dim light, but the complete absence of visible interaction with light. To answer that, we must move beyond the environment that shapes our perception. We must step outside the atmosphere that continuously bends and scatters light. Only then can we begin to understand what darkness really is, and why our everyday experience has quietly misled us. If we now move beyond the atmosphere that quietly shapes all our experience, the situation changes immediately and fundamentally. The moment we leave Earth's protective layer, we also leave behind the constant scattering of light that made our version of darkness possible. Astronauts often describe their first direct view into space in very precise terms. They do not report a gradual fading of light or a deeper shade of night. Instead, they encounter something far more absolute. The background of space appears as a complete void without gradients, without soft transitions, and without any visible structure. It is not very dark. It is simply featureless. To understand this, consider a familiar comparison. On Earth, even a weak light source can reveal nearby objects, because light interacts with air molecules, dust, and surfaces. This interaction allows light to scatter in multiple directions, making objects visible even when they are not directly illuminated. In space, this mechanism disappears entirely. There are no particles in sufficient quantity to redirect light toward the observer. As a result, visibility becomes extremely selective. An object in space is only visible if light from a source, such as the sun, reflects directly into the observer's eyes. If this direct path is absent, the object effectively vanishes, even if it is very close. Astronauts have noted that parts of their own spacecraft can become invisible when they fall into shadow, despite being only a short distance away. This leads to an important clarification. Darkness in space is not created by a lack of light sources. The sun continues to emit an immense amount of light, and stars remain active across the universe. However, light that does not reach the observer does not contribute to perception. In other words, light exists, but it is not seen. A useful teaching insight follows from this. Visibility depends not only on the presence of light, but on interaction. Without interaction between light and matter, there is nothing to carry visual information to the eye. Space removes this interaction almost entirely. This is the first genuine encounter with what we may call true darkness. It is not dimness, and it is not reduced illumination. It is the absence of any visible pathway between light and observer. Having established this, a deeper question naturally arises. Why does light fail to interact in such environments, and what does this reveal about the nature of space itself? To answer that, we must examine not just the absence of atmosphere, but the deeper structure of what appears to be empty space. If light is present in space yet remains unseen, the next step is to ask a more precise question. What is missing that prevents light from becoming visible? The answer lies not in the behavior of light alone, but in the nature of space itself. Space is often described as empty, but this term can be misleading. It is not perfectly empty, rather it is almost empty. In interstellar regions, the amount of matter is extraordinarily low. A typical estimate is about 1 atom per cubic centimetre. To appreciate this, compare it with Earth's atmosphere at sea level, where a single cubic centimetre contains on the order of 10 to the power of 19 molecules. The difference is not small, it is vast, beyond ordinary intuition. This extreme scarcity has a direct consequence. On Earth, light becomes visible because it interacts with matter. It scatters off molecules, reflects from surfaces, and is redirected toward the eye. In interstellar space, there are simply not enough particles to support this process. Photons travel along straight paths for enormous distances without encountering anything that can redirect them. A simple example helps clarify this. Imagine a beam of light passing through a dense fog. The beam becomes visible because countless droplets scatter light in all directions. Now remove nearly all of those droplets. As the number decreases, the beam fades from view, not because the light is gone, but because the interactions have vanished. Space is the limiting case of this process. From a physical standpoint, this tells us something important about visibility. Light does not illuminate space itself. It reveals objects only when interaction occurs. This idea aligns with classical optics and was emphasized in early studies of light by scientists such as Isaac Newton, who demonstrated that light becomes visible through reflection and scattering rather than by simply existing in empty space. A useful teaching insight follows from this. Darkness, in a strict scientific sense, is not defined by the absence of photons. Instead, it is defined by the absence of detectable photons reaching a sensing system, such as the human eye. In modern physics, this is consistent with how detectors work. Whether it is a human retina or a scientific instrument, visibility depends on receiving photons, not merely their presence elsewhere. Here is a useful teaching insight. Darkness, in a strict scientific sense, is not defined by the absence of photons. Instead, it is defined by the absence of detectable photons reaching a sensing system, such as the human eye. This shifts the definition from an external condition to an interaction between light and observer. This also explains why vast regions of space appear completely dark despite the continuous presence of radiation. The photons are there, travelling at the speed of light, but they pass through without leaving any visible trace unless they directly enter an eye or an instrument. Having understood this, we can now extend the idea further. If space allows light to travel without interaction, then what does this imply about the overall structure of the universe, and how objects are distributed within it? That question leads us to reconsider what we see when we look at the night sky. If space allows light to travel vast distances without interaction, then the next logical step is to examine how matter itself is arranged within this environment. What we discover is that the universe is not a continuous field of stars, but something far more structured and surprisingly sparse. When we look at the night sky from Earth, it appears densely populated. Thousands of stars seem scattered across a dark background, giving the impression of a crowded system. However, this perception is shaped by perspective rather than reality. The stars we see are relatively close in cosmic terms, and even then, the distances between them are immense. Consider the nearest star system beyond our own, Proxima Centauri. It is located approximately 4.24 light-years away. This means that even travelling at the speed of light, it would take over 4 years to reach it. Most stars are much farther apart. In fact, The average distance between stars in our galaxy is on the order of several light years. These distances create vast regions where there is effectively nothing at all. A useful way to visualize this is to imagine shrinking the Sun to the size of a small ball. On this scale, the nearest star would still be thousands of kilometers away. Between these points, there would be no visible objects, no continuous glow, and no background structure, only empty space. This leads to an important clarification. The universe is not filled with light uniformly distributed across space. Instead, it is composed of isolated sources of light, separated by enormous distances. Each star acts as a small island of illumination, surrounded by an ocean of darkness. Astronomer Carl Sagan often emphasized this perspective when discussing cosmic scale. He noted that what appears crowded from a distance becomes overwhelmingly empty when examined closely. This is not a matter of interpretation, but a direct consequence of how matter is distributed in the universe. A brief teaching insight can be drawn here. Human perception tends to compress large distances into manageable visuals. When we look at the sky, our brain interprets distant points as part of a single surface. In reality, these points are separated in three-dimensional space by distances so large that they defy ordinary intuition. If one were positioned between stars, far from any significant light source, the view would be fundamentally different from what we see on Earth. There would be no dense field of light, only a few distant points would remain visible, and everything else would be dominated by empty, featureless darkness. This understanding shifts our perspective in a crucial way. The brightness we associate with the night sky is not a property of space itself, but a result of our position within a localized region of stars. To fully grasp the scale of darkness, we must now extend our view even further, beyond individual stars, and into the space that separates entire galaxies. Now, when we extend this perspective beyond individual stars, the structure of the universe becomes even more striking. The spaces that separate entire galaxies are not simply empty. They represent some of the most extreme environments known in physics. Beyond the boundaries of a galaxy, matter becomes extraordinarily sparse. In intergalactic space, the average density drops to roughly 1 atom per cubic meter. To understand this, consider that even the most advanced vacuum chambers on Earth cannot achieve such low densities. What we are observing here is not just emptiness, but a condition approaching the physical limits of absence. This has direct consequences for how light behaves across these regions. Just as in interstellar space, photons continue to travel freely, but here the probability of interaction becomes even smaller. Light can move across millions of light years without encountering sufficient matter to scatter or reflect. As a result, these regions remain effectively invisible, not because light is absent, but because it never reaches an observer through interaction. Galaxies themselves, when viewed across such distances, appear as faint and isolated structures. Each galaxy contains billions of stars, yet from afar it reduces to a dim, diffuse patch of light. Everything we recognize, stellar systems, planets, and complex structures, is confined within these small regions. Beyond them lies an immense expanse where almost nothing occurs. A useful comparison can help clarify this scale. Imagine placing a small illuminated object at the center of a vast, unlit plane stretching endlessly in all directions. The object would be visible, but the surrounding space would remain overwhelmingly empty. Now expand this idea across millions of light years, and you begin to approximate the structure of the universe at the scale of galaxies. Modern astronomical surveys confirm this distribution. Galaxies are not spread uniformly, but arranged in clusters and elongated filaments, separated by enormous voids. These voids can extend for tens to hundreds of millions of light years, containing almost no matter at all. In practical terms, they are regions of near total darkness. Here is a key teaching insight. When we think about the universe, we tend to focus on visible structures. However, most of the universe is defined by what is not there. Emptiness is not a minor feature, it is the dominant condition. This naturally leads to a deeper question. If the universe contains such a vast number of stars and galaxies, why does their combined light not fill the sky with brightness? Why does darkness remain the dominant visual experience? To answer this, we must now examine the fundamental properties of the universe itself. At this point, a natural contradiction emerges. If the universe contains an enormous number of stars and galaxies, then logically, the sky should appear uniformly bright. Yet observation shows the opposite. Darkness remains the dominant visual condition. This question has been examined for centuries and is formally known in physics as Olber's paradox. The reasoning is straightforward. In an infinite static universe filled evenly with stars, every line of sight should eventually end on the surface of a star. Under such conditions, the night sky would not be dark at all. It would glow with a brightness comparable to the surface of a star. The resolution to this paradox lies in two fundamental properties of the universe. The first is its finite age. The universe is approximately 13.8 billion years old. Light travels at a constant speed, and therefore we can only observe objects whose light has had sufficient time to reach us. Regions beyond this observable limit remain invisible, not because they lack light, but because their light has not yet arrived. A simple analogy may help clarify this. Imagine standing in a vast forest at night, where each tree emits a small amount of light. If the forest extends infinitely, every direction would eventually appear bright. However, if the forest has a boundary, or if the light has not yet reached you from distant trees, large portions will remain dark. The universe behaves in a similar way. The second factor is the expansion of the universe. Since the work of Edwin Hubble, we know that galaxies are moving away from each other. As space expands, the light travelling through it is stretched. This process, known as redshift, increases the wavelength of light. Over great distances, visible light can be shifted into infrared or even radio wavelengths, which the human eye cannot detect. This means that even when light does reach us, it may no longer be visible. It exists, it carries energy, and it can be measured with instruments, but it does not contribute to what we perceive as brightness. Here is an important teaching insight. Darkness at the cosmic scale is not simply a local phenomenon. It is a consequence of time, motion, and the limits of perception. The universe is not only vast, but also dynamic, and these properties directly shape what we are able to see. When we combine these factors, the finite age of the universe and the continuous stretching of light, we begin to understand why darkness persists, despite the presence of countless luminous sources. This brings us to a new boundary of understanding. If much of the universe is either too distant or too altered to be seen, what happens when there is no light reaching the observer at all? To explore that, we must now turn from cosmic structure to the limits of human perception itself. At this stage, we shift from the structure of the universe to the limits of the observer. Up to this point, darkness has been explained as a consequence of physical conditions, distance, lack of interaction, and the behavior of light. However, there exists another boundary, one defined not by space but by human perception. The human visual system is highly sensitive. Under low light conditions, it can detect remarkably small numbers of photons. In controlled experiments, it has been shown that the eye can respond to just a few photons under ideal conditions. This sensitivity is what allows us to navigate dim environments and detect faint stars in the night sky. However, there is a limit. If no photons reach the eye at all, the visual system has no external input to process. In such conditions, vision does not simply turn off. Instead, the brain begins to respond in a different way. To understand this, consider how the brain typically functions. It continuously interprets signals from sensory organs and constructs a coherent representation of the environment. When those signals are reduced, the brain compensates by amplifying what little information is available. When the signals disappear entirely, the brain may begin to generate patterns on its own. This phenomenon has been observed in conditions of complete darkness or sensory deprivation. Individuals report seeing flashes of light, geometric patterns, or vague shapes, even though no external light is present. These are not perceptions of real objects, but internally generated activity within the visual system. A useful comparison can be made with sound. In a completely silent environment, people may begin to hear faint ringing or tones. This does not indicate an external source, but rather the brain responding to the absence of input. Vision behaves in a similar manner under extreme conditions. Here is an important teaching insight. Perception is not a passive recording of reality. It is an active process. The brain does not simply receive information. It interprets, fills gaps, and, when necessary, creates its own signals. In the absence of external input, this process becomes more apparent. This means that in the deepest darkness of space, where no photons reach the eye, what a person experiences may not be true visual emptiness. Instead, the mind itself may begin to introduce structure where none exists. This introduces a new dimension to the concept of darkness. It is no longer defined solely by physical conditions, but also by the limits and behavior of human perception. With this understanding, we are led to consider not just how darkness appears, but how it affects the human mind. What does it mean to experience a vast, empty void with no visual reference at all? That question takes us from the physics of darkness into its psychological impact. When perception begins to operate without external input, the experience of darkness changes from a physical condition to a psychological one. Up to this point, we have examined how light behaves and why it may fail to reach the observer. Now, we must consider how the human mind responds when confronted with that absence. Throughout human evolution, darkness has been associated with uncertainty and potential danger. In natural environments, limited visibility reduced the ability to detect threats, making caution a necessary response. Over time, this association became deeply embedded in human psychology. Darkness was not simply a lack of light, it became a signal of vulnerability. However, the darkness encountered in space is fundamentally different from the environments in which these instincts developed. On Earth, darkness often conceals objects. In space, particularly in regions far from any light source, there may be nothing present to conceal. The environment is not filled with hidden threats, but with an absence of structure altogether. This creates a unique psychological condition. Astronauts who have observed deep space describe a sense of profound isolation. The absence of visual reference points removes the usual cues that help us orient ourselves. There is no horizon, no familiar scale, and no nearby objects to provide context. As a result, the mind is left without its usual framework for interpreting space. A useful comparison can be made with standing in an open landscape at night. Even in darkness, the presence of the ground, distant lights, or the outline of objects provides some sense of position. In space, these references disappear entirely. The observer is surrounded not by darkness that hides, but by darkness that contains almost nothing at all. Psychological studies of isolation and sensory deprivation provide insight into this experience. When individuals are placed in environments with minimal sensory input, they often report feelings of disorientation, anxiety, and a heightened awareness of their own thoughts. The absence of external stimuli shifts attention inward, sometimes leading to an intensified perception of self. Here is a key teaching insight. The human mind is adapted to environments rich in information. When that information is removed, the brain does not remain neutral. It actively responds, often by amplifying internal processes. In the context of space, this can transform a simple absence of light into a powerful psychological experience. This explains why astronauts often describe not fear of specific dangers, but a deeper awareness of scale and existence. The vast emptiness does not threaten in a direct way, but it reveals the relative smallness of the observer within the universe. Having examined this psychological dimension, we are now prepared to consider the most extreme manifestation of darkness known in physics, one where light itself is no longer able to escape. Building on this psychological and physical understanding of darkness, we now arrive at its most extreme and scientifically significant form. There exist regions in the universe where darkness is not merely a result of distance, absence of interaction, or limits of perception, but a direct consequence of gravity itself. These regions are known as black holes. They form when massive stars collapse under their own gravity at the end of their life cycles. As the collapse continues, the gravitational field becomes so intense that it alters the very structure of space and time. At the boundary of a black hole lies what physicists call the event horizon. This is not a physical surface, but a point of no return. Once any form of matter or radiation crosses this boundary, it cannot escape back into the surrounding universe. This includes light itself. To understand the significance of this, recall that visibility depends on light reaching the observer. In all previous cases, darkness resulted from light failing to interact or reach us. In a black hole, the situation is more extreme. Light that approaches too closely is permanently trapped. It does not scatter, it does not pass by, and it does not emerge. It is effectively removed from the observable universe. This leads to a unique visual outcome. A black hole appears as a perfectly dark region, not because it lacks light sources nearby, but because it prevents any light from escaping. Observations from instruments such as the Event Horizon Telescope have confirmed this structure. Surrounding a black hole, there is often a bright ring of heated matter emitting intense radiation, while the central region remains completely black. A useful way to think about this is to imagine a region where every path that light could take bends inward. No matter the direction, the trajectory leads deeper into the gravitational field. As a result, there is no possible route for light to reach an external observer. Here is an important teaching insight. Black holes redefine darkness. In all other contexts, darkness is linked to absence or limitation. In this case, darkness is enforced by physical law. It is not a passive condition, but an active result of gravity controlling the behavior of light. This also highlights a deeper principle in physics. Light, often considered the fastest and most fundamental carrier of information, is not universally free. Under extreme conditions, even it is subject to constraints. With this understanding, we reach the most absolute form of darkness that can exist within the current universe. Yet even this is not the final stage. To complete the picture, we must now consider how the universe itself evolves over time, and what that implies for the future of light and darkness. Having examined the most extreme forms of darkness that exist today, we now turn to a broader and more fundamental question. Is darkness a temporary feature of the universe, or is it its ultimate state? To answer this, we must consider the history of the universe itself. Shortly after the Big Bang, the universe was not dark at all. It was filled with intense radiation, a dense and hot environment where light was constantly interacting with matter. As the universe expanded and cooled, it entered a period often referred to as the cosmic dark ages. During this time, there were no stars yet formed, and although radiation existed, there were no luminous structures to illuminate space in a way we would recognize. Eventually, gravity led to the formation of the first stars and galaxies. These structures introduced localized regions of light, creating the universe we observe today. At present, we exist in what can be described as a luminous era, where stellar processes continuously generate visible radiation. However, this phase is not permanent. Stars rely on nuclear fusion, a process that converts mass into energy. Over time, this fuel is gradually exhausted. Smaller stars may persist for billions or even trillions of years, but eventually, all stars will reach the end of their life cycles. When this occurs, the primary sources of visible light will disappear. Galaxies themselves will also evolve. Interactions between them will alter their structure, and the rate of new star formation will decline. As fewer stars are created, the overall brightness of the universe will diminish. This is not a sudden transition, but a gradual fading over immense timescales. A further development involves black holes. While they represent the most extreme form of darkness, they are not eternal. According to theoretical predictions by physicist Stephen Hawking, black holes emit a form of radiation and can slowly lose mass over time. This process, known as Hawking radiation, implies that even black holes will eventually evaporate. A useful teaching insight emerges here. The universe is not static. Its large-scale properties change continuously over time, and these changes determine the balance between light and darkness. What we observe today is only a temporary stage in a much longer evolution. When all stars have exhausted their fuel, and when black holes have evaporated, the universe will enter a state often referred to as heat death. In this condition, there are no significant sources of energy, no ongoing processes that produce light, and no structures capable of sustaining illumination. The universe will be cold, dilute, and effectively dark. This leads to a final conclusion. Darkness is not an anomaly that needs explanation. It is the natural outcome of the universe's evolution. What we experience today, regions of light scattered across vast emptiness, is a brief phase between a luminous beginning and a dark future.